All right, hello everyone. So today we're going to continue our discussion on LStore and to really study the core of this lineage-based storage architecture, which is going to be the basis for our first, second, and basically the entire semester. So we talked about the overall architecture is that we have a set of base pages, and these base pages internally are set of pages, and those pages, one for each column. And a set of base pages is when the record is initially inserted, they go to the base page, they get a read, that's a stable read, that read never changes. Now, if that record ever gets updated, then there will be a corresponding tail page, and the updates will be appended to those tail pages. And periodically, so we have base page, tail page, periodically they get consolidated, and we get these consolidated merged pages. So this will help us the future read to avoid the going back and forth between the base and the tail. And also there is an indirection layer, and this indirection layer indexed by that base read. And you can think of this as also a logical read, as a stable read, and all the indexes point to this original read of the insertion. And the importance of this is a stable, that means it doesn't change, meaning when a record gets continuously updated, we get a new tail record, but the base record does not change. So if as long as the indexes are pointing to this stable read, or as long as all our internal referencing or data structure within the database utilize this stable read, we can always, from that stable read, we can figure out where is the latest version of the record is, and from the latest version of the record, we will have back pointer to the previous version of that, and so on. So we can look at the entire history of a record. And so there is a need of a mapping of a base read to or a base read to the normal read, or to the tail read, the latest version of the record. And so this mapping could be an external data structure, or it could be part of the it could be a column of the table potentially. So that's the general design. That's the general architecture of this storage model. And so now, if you don't have any questions, if you do, please ask me. And so now we're going to go into more details on how this actually works. Okay, so as we talked about and also mentioned in your assignment, what we also have is a columnar storage. That means every column will have its own page. And so here, what I'm showing here is columnar storage for 5 columns. So there are 5 columns, each have its own page. And these are sort of logical. This could internally be 5, 6, 4K pages. And this could be 2, 3, 4K pages. This could be also 5K pages. And this range is for a page range or a partition. And this could represent 10,000 records. And 10,000 record for the first column, which has a certain size, could translate to 5 pages. 10,000 record for the second column, which has a different size or maybe compresses better, could translate to 3 pages. And so why this is these base pages have of different size for each column, just because of that property. And so this is, you can think of this as one page range. This is another page range, and this is another page range. Or so essentially what we're doing a range partitioning. So we take our records, we divide them into a set of ranges, and this partitioning could be just as simple as saying, okay, divide your database into ranges of 64,000 records or 10,000 records, whatever that number is right for that particular workload. So I think for your assignment, you can experiment, you can do a 64,000 or even larger. And for each of these partition, for each of these ranges, we have a set of corresponding tail pages. So that means any update that goes to these pages will always be added to these tail pages. Any update for these pages will always be added to these tail page. So for example, this is a record. A record is defined as almost, you can think of as an array that is span all the base pages, and it's aligned. And it's aligned in a sense that if this is, let's say, the fifth record in this page range, it is the fifth element, it would be the fifth entry or fifth slot in the first column, it would be the fifth slot in the second, in the third, in the fourth, and in the fifth. So this is aligned. And now, if this record this is the originally inserted record, this record will have, this position will be associated to a physical stable read, will be associated to a stable read or a lid. So I'm using the word stable read and a lid interchangeably here. So this will be associated to a stable read. And if this record ever gets updated, the update will be added to the tail page. And again, tail page would have the same property. It would be a cross set of tail pages. And if this is like the, say, the seventh tail record, it will be the seventh element in the first one, a seventh element in the second one. Well, if this column has never been updated, we don't have to even have any footprint of that, and it would be the seventh element in the fourth column. And again, the fifth column never updated. I mean, there's no even, technically, we don't even need to have allocation of any pages for it. So these tail pages are allocated on demand. Now, every record, whether it's on the base page or if it's on a tail page, they're all represented by a read. And all of these pages are included in our page directory. So tail pages, base pages, doesn't really matter. At the lower level that we're dealing with just simple pages, it doesn't really matter whether they're base or tail. They all have read, they all are just a bunch of pages, and the records in them all have reads, so they can all be included even in the same page directory. So again, that's one level deeper into this, into the design. Again, please, I'm going to pause if you have any question before I go to the next slide.
So it says they're handled identically at the storage layer. Does that mean they have to be in the same data structure, the base pages and the tail pages?
So since they are identical in them, there's not really any differentiation. So what you would do in a typical sort of enterprise or commercial implementation of this, yes, you wouldn't change as far as the page directory concerns. These are all identical, and that's a really powerful aspect of it, because there's a lot of these are really heavy lifting and sort of core of any system. So you don't want to keep adding, customizing it in a sense that you want to make it specialized for this and then make another specialization for something else. You want to make this as primitive and as uniform and sort of really just an abstraction so that you can be used for any purpose. So that would be the ideal implementation. But for the purpose of your assignment, we'll kind of give you that, you have that freedom, you have the choice of whether you want to use the same set of data structure for both of them, you want to use the same page directory for both of them, you don't want to use that. So that kind of would be a design choice and design decision that you make.
Thank you so much.
And the justification for that would be is that simplification. So you have full control on that.
I have a question. So it looks like to me that each base page has a tail page or more, depending on how many updates are done.
Exactly.
But then in the milestone 1, I read that we initially start with a single tail page. Any updates to these 16 base pages are appended to this tail page. So is there one tail page per base page range, or is it one tail page per base page to start with?
Yeah, so each of these are a page range. This is 1 page range, 2 page range, 3 page range.
Okay.
And so a single range could itself internally have 5, 6, 10 base pages. And for as a whole, each range is correspond to 1 tail page.
Okay, so each of the orange blobs corresponds to a base or a tail page that is like unified.
Yeah, so this you can
Okay.
think of this is a page range, consists of 5 base pages, and any update of these 5 base pages in this page range will go into this orange blob, as you said. And initially we will have 1 orange blob because we only got it. Once there's an update, we'll create 1 orange blob for it. And we start filling that up. But as you also mentioned, is that, well, these records could be get updated millions and millions of times. There's no limitation on that. So this first page that we created as a tail eventually gets filled. So I create another one, then another one, another one, and you create it as much as long as there is need for it. So completely on demand. So concept of a page range. So we range partition our record into these page ranges. Each page ranges consists of set of base pages. And the granularity of a tail page could be at the level of the table, meaning any base pages that I have, any update to the entire table could go into 1 tail page. So that's one extreme. The other extreme is that I will have a tail page for every single base page, so that any update to that base page go to its corresponding tail page. So this is 2 extreme. In one extreme is that I have a tail page for the entire table. So that means all the updates are going to the same page, enormous amounts of contention, locking, and so forth. So it's gonna make that page really hot, and it's going to deteriorate the performance. The other extreme is that for every base page, I'm going to allocate a tail page, but then a single base page may not get that many updates. So I'm end up going to have many unfilled tail pages. So it's not going to be a good use of space utilization. So the middle ground is, well, instead I am going to, for a set of base pages, I am going to direct their update to 1 tail page. So that's the middle ground. And so the granularity of the tail page could be at the table level, could be at the page level, but what we're doing is to make it at the granularity of the page range, meaning make it the granularity of set of base pages to make sure the page is not too hot, and also to make sure that the space is not underutilized. For these set of base pages, there's going to be enough update that more or less that page remains at least maybe 50% full. So the page is not that is only a single update in it and the rest of the page is always empty. So that's a rationale behind that, why we have page ranges and why we assign tail pages to them in that fashion. Does that make sense?
Can I ask a question?
Absolutely.
Can you explain, because if we get the record, the RIDs only specify which page is in it. How could we determine which page range it is? Do we need to keep track of the logical ID of like this is the fifth record or something to determine which page range it is? Like, how can we determine which page range it is?
So given a read, how do you figure out which page range it is? Is that the question?
How did you figure out which page range it is?
Well, first of all, this could be, so you could have this logic embedded as just a piece of, so this could be like maybe just almost a static knowledge. I mean, one way of thinking about it is that, you kind of, let's say in the most basic way, you kind of hard code it, that's saying that every 64,000 belong, so the size of the page range is 64,000. So any read that I get between 0 to between 1 to 64,000 is going to belong to the first page range. If I get 78,000, well, it's going to belong to the second page range. If I get 137, well, it's going to be on the third one, and so forth. So that's to figure that out. That's so that would be kind of straightforward in that sense, which base page it belongs. And you can also, as the page directory, so what you could index, for example, here is that I say the first page contains, the first base page has 10 reads in it. So in my page directory, I could say read 10 pointing to this first base page. And then I could say the second base page has another 10 reads in it. So then my page directory, I say read 20 points to the second page, and so forth. And then I kind of construct my page directory in that manner. So if I'm looking for a read of 14, then I go to my index, and it becomes like a tree lookup or an index lookup, is that, well, the first page is not going to be, is everything under 10, and the second page is everything under 20. So this is going to fall within that range. So I know which base page I need to go to. So I can now find that base page that holds that particular read that I'm looking for. And also the information of which page range is belongs to, that something could also be added dynamically into the page directory. So that for each entry, which is what is the end read, or what is the starting read of a particular page, or maybe what is the range of a read that spans a single page. And we could also incorporate there or add there how much, if there's any empty space in that page, or you could also add which page range this page belongs to. So you could have some metadata for every entry in the page directory that provides you those additional information. So that could be another method, assuming all your reads are logical. Because if the reads logical, then you need this. You need a mapping of how do I go from my read to the actual page. But you could also have a simpler design that your read, even what your read is. For example, if your read is 20, then you already know that each page contains only 10 reads, and you know what's the starting point of, for example, even if you had, if your data was stored as a file, you know that your read is, if you're looking for read 13, you know each page only contains 10, so you directly know that you need to jump to the second page. And since it's all fixed size, even within that second page, you know exactly where you need to look. And if you have one file maybe for every column, so you have 5 files, then you can do 5 lookup to get all 5 column of that record. So your read could have sufficient information in it to allow you to do that, to be able to determine exactly where it lies. Or it may not. And to get the actual physical reference of where it points to, you need to have a page directory that, given a page ID, or the red will give you where is the physical location of that record. And in this case, given a page ID, it could also give you all the physical location of all the pages for all the columns. So here, that one single entry wouldn't just give you the first column, but it also give you the second column and third column and fourth column and the fifth column. So again, that could all be extracted from the page directory.
Okay, thank you.
Any other question? And again, a lot of these are, there's not just one way of doing it. So there's many different ways of doing it. And so, and then you have full control, you have full freedom to figure out what would be the best way for you and what do you think is the right design. And so you can really have that exploration. So in terms of the idea of page range or and the reason I'm kind of using a couple of terminology here and there is just because that's the terminology also used in the literature. So page range is a term that is used. Range partitioning is something that is used. So these are all kind of almost a standard terminology. And so one other use cases of or typical usage of page range or especially range partitioning is that if I have a lot of records and my data won't fit in a single machine, so then I can partition my data based on the ranges. So I can say the first 1,000 records go to this machine, the second 1,000 record goes to the second machine and third machine. So I can now split my machines across, split my data across machines. So that's that topic, that method is available in most database systems. And they also have hash partitioning. So range partitioning is kind of a contiguous set of records. You could also have a hash partitioning. Hash partitioning is just a randomly, any record, it gets randomly assigned to one of the machine. And there are pros and cons to it, to both of those partitioning techniques. There's alternative, there are other ways of doing it too. I mean, the range partitioning could also, doesn't mean necessarily with respect to the read space. The read space means that space that I take the reads from 1 to 3, like the integer values, that's considered read space. And also that uses the key space as well. Your key space could be integer, your key space could be strings, depending on the data type. So there could also be other factors. For example, if you are, this is a kind of a classical example in this, if you're creating a dating website, most likely the people in one town, most of the dating will happen within that. So most of the interaction between that, those members going to be co-located within a single town. So if I'm partitioning my data, I put Davis into one machine, maybe San Francisco another machine, and Santa Cruz in a different machine. So that will be one way of doing partitioning. This kind of partitioning may not be so well suited, for example, for social network like Facebook, because we tend to have international friends. We communicate with a lot of different people, potentially across globe. We will probably be more targeted to to the place that we live. But as we go to our new jobs or go to school, and so we kind of get to know other people in other part of the world. And so different kind of strategy would apply. And also you would have all these anomalies. For example, you have these famous actors or politicians who have potentially millions of followers. So that would really causes problems. So for example, for those people, instead of maybe for an average person, you could have thousands of them handled by a single machine, but you may actually have multiple machines or maybe tens of machines to handle a single popular person, because the load and to handle all the viewers and all the interaction, it's a lot more. So again, those are other ways of partitioning the data, but that partitioning the data is a very sort of a standard way, it's a standard topic. Any other question? Okay. So kind of a detailed view of this. And again, I'm kind of keep going over and over till make sure everybody really get the idea behind the Ulster design. So again, we have columnar store. These are different columns. So we have 5 columns here, and our data is divided into ranges. So we range partition the data, and we consider these as page ranges or range partitioning as a result of that range partitioning. And and these are the base pages. So these are when the records initially added to the table, they are added to the base pages. They are going to be read-only. We're never going to modify a record that is written here. And it's also going to be compressed. For the purpose of this assignment, we're not going to compress it, but in a real system, they will be compressed for all the benefits that we have previously described. And for every page range, there is corresponding set of tail pages, and a base page itself may contain several base pages internally. So page range is an abstraction, and a base page is one level deeper in that abstraction, and regular pages, you can think of it as the final level of abstraction. So the most primitive is base page. The most primitive is just pages. And so for one partition or for one range, any update that goes to this range, they will have their corresponding tail pages, and all the writes will be appended here, and we'll keep them as uncompressed. Eventually they can be compressed, but in the immediate window of time, they will be kept uncompressed. So a base record is a spans over a set of aligned columns in a base page, and a tail record is a record that spans across a set of aligned tail pages. And so that's that. And as we kind of fill up as we kind of add tail records, we eventually, as was also asked earlier today, is that the tail page gets filled up, so we have to allocate new pages, new tail pages. Our base pages, they're not going to increase in size. Once they're written, once they're compressed, they're done, we're fixed. But our tail pages for that range, well, we keep adding updates and more and more updates, so we need to allocate more and more pages as needed. So this could grow potentially infinitely, versus that the base pages in that page range, they're fixed. Once the page range is established and is filled and done, then that will never be ever changed. And then we talked about that indirection column. So you can think of now indirection column as yet another column in our base pages, and also another column in our tail pages. So what is stored in the, the read in the base page has stable read. So that means once I add the record, the read that I receive, that becomes the stable read for that record that will never change. So I will always refer to that record using that read that was assigned to it at the time of insertion. And I will have this column, which is that indirection column. So now if I want to find out the latest version of the record, I come to this indirection column. So if this was the 5th, this is a read 5, that means it's a 5th element in the first column, 5th element in the second column, 3rd, 4th, and 5th also means it's a 5th element in that indirection column. And so if I'm looking, if I want to get the latest version of the 5th record, I know I do have a base record for it, but to figure out if there has been ever an update to this record, I can come to my indirection, and from my indirection, I will do a mapping of my base read or my stable read or my lid, because it comes also at some point becomes logical, because this record has many other versions and many other RIDs associated to it. So that's why, in a sense, it's also not only is a stable RID, but it's in a sense it's also a logical RID. So I come to the base RID, and then I figure out what is the latest version of this record into the tail pages. So essentially, what is maintained here, I hold the RID of the last tailed record associated to this base record. And if I were to update this record and add a new version, well, I go ahead and write that new tail record, and then I have to do one more thing, which is I need to do an in-place update in that indirection column to point to the latest version of the record. Before it was pointing to the first version, now it's pointing to the latest version. There's also, again, the tail pages are an identical copy of the tail pages, of the base pages. So there's also an indirection column in my tail page. And what the indirection column in tail pages does, instead of being a forward pointer pointing to the latest version, they have a backward, they act as a backward pointer, which point to the latest version of the previous version of the record. That means this indirection entry holds the previous RID of this record, versus that this indirection entry holds the RID of the latest version. So again, they're identical in that sense too. What stores in the indirection column is just RIDs. Here is the RID of the latest version. Here is the RID of the previous version. So that's the basic sort of kind of the basic structure.
So the oldest update, does that point back to the base page? The oldest update.
Which update?
So the newest update, right, is what's pointed to by the base page.
Exactly.
And then the latest update points to the previous update.
Exactly.
If the previous update was the first update done, does that one point back to the base page?
It could. So that's a good point. And so there might be some usefulness to it. And yeah, so that you could do. And why is it kind of so its usefulness comes in sort of later stages when we're kind of doing with the merge. But probably an easier solution is that it might be even more beneficial that we have yet one extra column in our tail pages to hold which RID this record belongs to, what is the base RID that this record belongs to. Because otherwise, as you said, if I'm just looking at these tail records, I don't know that they're associated with this. If I'm coming from this record, I can follow up here and figure out which base record is associated to this tail record. But if I'm just looking at these tail pages, I have no idea. So what I could do, I can go to the previous version and then the previous version, and as you said, the very first version of that, if it points back to the original RID, then I know all these tail records that I just scanned belongs or are the updates of this particular RID. So that's a useful information to have. But in order to do that, you have to do multiple sort of lookup. So alternative to that, it might not be a bad idea to actually have a column in our tail page to specify which base RID each tail record belongs to. So kind of right here, this is the fifth base record, this is the fifth base record. I kind of repeat that information. And again, there's a trade-off between those two. But it's definitely useful to have that information in the tail pages. Otherwise, we cannot just look at the tail pages independently to figure out what each record belongs to.
I have a quick question.
Sure.
Just to clarify, a new RID is assigned for each base record, and each modification, or it's only for the base?
Yeah, so every time you add a record, a RID is assigned. Adding something to a base page constitute as a record. Adding something to a tail page constitute the same to also as a record. They're all pages. They're all records. They will all have RIDs.
Okay, thank you.
And that's where we're kind of at the lower level. There's this uniform abstraction. Is that we're just dealing with pages, RIDs, page directory. And that's it. These tail pages, these base pages, these page ranges, or this differentiate between a base RID or a tail RID or a stable RID versus non-stable RID. These are kind of just higher level concept. But at the low level, we're dealing with pages, RID, page directory. And that's really important. At the lower level, it's very, we have this same abstraction is sufficient to implement everything that we're talking about. So this update to the schema, I mean, if you're referring to the schema encoding, yes, so the schema encoding will be just another column, a metadata column, like the indirection column that is added. So now this is kind of now getting to the second milestone. This is one of the main pieces of the second milestone. So as we kind of add these tail pages, so now the question is, can we go back and consolidate existing tail pages that are done and bring it back to our base page? So do that consolidation step. So what happens is, as a background process, completely background without interfering with the foreground transaction, we take a set of tail pages that are filled and also a set of tail pages that all the records written to it have been committed, and they add them to a merge queue, something to be merged whenever there is time, whenever there's a resources available for the system. There's not too much thing to do at that point to do this merge. So periodically in the background, we take a base page and a corresponding tail page, and this, what's included in this tail page is a set of committed record, a set of consecutive committed record. That means if I start from so for my base page, I start with the record 1 as a tail, record 2, I do first update, second update, third update. I go all the way to, I do 10 updates, and I can only fit 10 updates into one page. And then I go to my second page, 11 update, 12 updates, so I get 20 updates. So 20 updates, 2 pages. All of them are committed. These are done by the transaction that are committed. So that means for these 20 records or these 2 pages, there's never going to be ever that, I mean, I'm not going to ever modify these records anymore, these tail records anymore, because they're committed, they're finalized, they're done. And if the record ever gets updated, the same record gets updated, it's not going to affect these 2 pages, because they're just going to be add new tail records, and we're going to add a new tail pages. So then if a set of record has been committed, a consecutive set of record that are committed, then they become eligible for a merge. So then they can trigger a merge process. And what the merge process does, it takes a set of base pages, and by design, we know our base pages are read-only, because once we construct these base pages, we're never going to change them. They're about the physical data, no one's going to do an in-place update on these base pages. And then we know that these tail records are also append-only. These are all committed. They're stable. So this is a stable set of pages. This is a stable set of pages. So completely in the background, we can go ahead and merge them and create a new consolidated base page that reflects the update in those tail pages. And so let me just actually pause. So I take one tail page or one set of tail pages from my queue, and then I do a background merge, and I create a set of new base pages, which is going to get it's going to replace these because they're identical to these, plus the fact that it has seen all the recent updates up to this point, let's say. It doesn't have every single update. It has a set of updates. It doesn't have every single update. It has a set of updates.
Professor?
Yes.
So are you saying that the merge file replaced the base page itself, or it just makes a new page record? And
I'll get to that part. I'll get to that part. So let's just say right now, so let's look at the concept of creating this consolidated base page. This updated base page that contains a set of recent updates, a set of recently committed updates. Doesn't contain every single update. There might be some updates that is not here. For example, for this example, this is the circle. This is the region. After that region, there are some updates here, or even just this record. There's this update here. It doesn't include that. It just includes just a bunch of updates, a bunch of committed updates. And then we write a new set of base pages that reflects the changes that was done here. So up to this point, does that make sense?
yes.
Perfect. So let's then we walk through it step by step. So now the other interesting point that we have, and this is what the word lineage in the designs come from. Each base page that I construct, whether the original one or this consolidated base page, they have what is called an in-page lineage tracking. This page in its header, it writes down how many updates have it been applied to this page. So the original base page that I create, that in-page lineage value for it is 0 because it was the original base page, and there haven't been any merge, there haven't been any reconsolidation. So the in-page tracking of it is 0. But the moment I come here and I take that base page and apply 20 tail records to it, 20 committed tail records to it, any resulting merged pages or any resulting consolidated pages that was created from that process will have an in-page lineage tracking of 20. So if I'm looking at these base pages, I know that the first 20 updates, whatever they may have been, have already been applied to it. When I look at this base page and I see this lineage page, lineage information is 0, that means no updates have ever been applied to it. So does that concept make sense? Now how it's used, I'll come to it, but kind of building this step by step.
Professor, do you delete the tail records that you consolidated?
I'll come to that. Those are excellent questions. I'll come to all of that. But that's kind of what I discussed so far. Is that makes sense? So whenever I find a set of consecutive committed set of records, those tail pages become eligible to be merged. They will be added to the queue, and whenever there is some free cycle, there would be another thread that looks at the merge queue and says, okay, what's the next tail page to be merged? And it just grab one of those and go ahead and does the merge. And so that's also answering that question on the chat.
Okay.
So now we do this merge, we create this consolidated record, and crucially important, this very basic idea of maintaining an in-page lineage for the pages that we create. This lineage information is so crucial, and we see why. Okay, so now let's look at our page directory. So our page directory is that it's pointing to our base page, and this is the original base page, and it has a lineage information of 0 because it hasn't been updated. Then this is its corresponding tail page, And this corresponding tail page had been selected to be merged, and it was added to the merge queue, and then the merger thread had grabbed it and had asynchronously merged the base page with that tail page, and it resulted in a consolidated tail page. A consolidated base page. And it has now a lineage information. The lineage information of this was 0, and if this is assumed there were 37 records, then the lineage information of this will be 37, because this consolidated page has seen 37 updates so far. And okay, so now let's see what happens. So this has happened completely asynchronous lazy merge. So this is completely asynchronously happened in the background. So in the background, we took a base page, we took a tail page, we constructed this consolidated page. And this has no effect on the foreground transaction. So background is something that we do it in the background. Nobody needs to be aware of it. And the foreground is the transaction, the user transaction that are being executed. This has no impact on what the user transaction is doing. It's not going to block them in any way to do this first part. So then what happens is once this page is ready to go, the only thing that needs to happen is that I need to make my page directory that was pointing to this page now to point to this instead. That's the only thing that needs to happen in the foreground. So basically, the page directory now begins to point to this page, and the old reference of the page directory, which was to the old record, to the old base page, is removed. So this dashed line, so it used to be pointing to this. Now the page directory points to this new page. I am not going to deallocate this old base page because there could be some other queries that have already went to the page directory and have a reference to this page, and they may be reading it. And I don't want to, I neither want to kind of have all this pin count, like for example, we talked about in the buffer pool, to figure out how many people are still reading this page and kind of deal with all the concurrency issues. And so we don't want to do that. So we basically say, well, we're just going to keep this old page around because there is a possibility that there's some queries that are still accessing it. There's some transactions are getting access. So we're going to keep it around. And what we're going to do, we're going to eventually drop it, but we're going to do it in a clever way and also a very simple way. So the way we're going to drop this page is that we say, when we started the merge, what are the queries that were running when we started the merge? And so before we started the merge, any query that was running, they could potentially had access or reference to this page. So that means they may be reading that page. So as long as there is a query that has started before the merge and is still running, it's possible that they have access to this page. So as long as there is a query that started before the merge and is still active, we're going to keep this page around because that query may have reference to this page. But as soon as there is no more active query that is started before the merge, then there's no other way that anybody would have access to this because all the new query after the merge, they're all going to get from the page directory to the new page. So there's no one that's going to have any reference to this older page. So at that point becomes safe to simply remove it without causing any concurrency issue. So the deallocation problem is solved by this method. Now I'll come back to some of the questions with the tail pages, but let me there's another important thing here. So does this part make sense? So when the merge page is ready, all I do in the page directory, it points to the new base page, and the old base page are still kept around, and I will only deallocate it or drop it when there are no queries that could possibly access it. If I'm certain there's no more queries that could potentially have access, are still accessing this, then that's a safe point to drop it. And a simple answer, we're not going to drop any tail records. So and then I will explain why that is the case. Eventually things can be dropped, but at the times, and it's so crucial for this merge to happen without any contention, without the needs of complex concurrency control, is that we always operate on stable data. This base page is stable, is not changing. This tail page is committed, is stable, is not changing. So the entire merge process is happening on the stable data. So at the time of the merge, when I'm ready to modify my page directory, this was a stable, this is a stable, and all is happening in the foreground. The only action is happening in the foreground is a single pointer swap or a location swap in the page directory. That's the only concurrent action that is happening in the foreground. Now, if I were to decide at the same time I drop my tail pages, now I could have potentially a concurrency issue. Why I could have concurrency issue? Because if at the time of the merge I try to drop my tail pages, it is possible that some base record, some queries looking at this data, and they want to use the tail pages that have already been reflected into this to try to get the latest, try to bring the data in this base page up to date as part of the query execution. Now I'm going to have a concurrency issue. So tail pages cannot be dropped at least for certain amount of time till everything settles. Only when everything is settled, only when I know that something not going to ever be touched or accessed, that's when we start doing the processing. That's when we start doing cleanup. That's where we start to do consolidation. So we do the merge consolidation when I know the set of merge tail records are stable. They're not going to change. They're stable. And I will remove them when not only for the tail record, I will remove them. Not only I know that they're stable and they're committed, but I also know they've already been merged. And also I know nobody else is going to access it because already that information is reflected, for example, in the base pages. So there's no need for them. So I can now, without needing to kind of locking them or flagging everybody, I'm going to remove this stuff. I can go ahead and drop them. And to do things in a lock-free or in a latch-free manner, we have one basic construct. We go back to hardware. We say, what does the hardware right now can efficiently support? The hardware can support a single pointer swap, a compare swap, a CAS operator, compare and swap operator. That means it can support a single action. Changing the page directory, pointing to the new one versus the old one, that's a single action. But changing the page directory at the same time, dropping a tail page or dropping this, that's not a single action. So every single sequence of the protocol of all the operation is designed in such a way that I can do one single operation on stable data. And that will ensure that the sort of the overall, sort of the broader goal and the overall system can have this sort of the latch-free design property. So every sequence of the operation is important to ensure that overall goal. So I'm going to make a pause before I go to the next step of this. See if you have any question.
I have a quick question about if say the pointer swap has happened. We haven't deallocated the original base page yet because someone has a query open on it or whatever. What if that query is an update? How do we reconcile that?
Okay, so that's perfect, and that's the next thing that I'm going to discuss. That was the exact next topic. Any other question? Okay, so let's answer that question. So right now we have we did one swap. So we took this page, we took that page, we created a consolidated base page, and then we did a pointer swap, and we put this into the allocated queue. Okay, so now let's look at another case. Now let's say I want to merge this base page with this tail page, and I kind of do this in the background. And then I create this consolidated base page with its lineage information. And remember, so now this is the important part. When I'm selecting a set of tail pages to be merged, these are consecutive committed set of tail records, meaning these tail records are not going to change. These are stable. So that means for this page range, these are all the updates that it has. And I'm going to just take a set that are committed. I'm not going to take everything. So for example, there is this particular record here that it's not included in that. So that means this set of tail pages that I'm taking for updates only contains for this particular record, it only contains the first update. It doesn't contain the second update. And that's fine. And that's by design. So the result of this merge, it only contains the first update. It doesn't contain the second update. So that's the first point. So is that clear? So when I'm selecting a set of tail record, again, I go back to the point, it has to be consecutive set of committed tail records. And it may or may not be everything, and that's fine. It's it's a lazy merge process, and it's forgiving. It doesn't have to by design. We don't want to enforce that when the merge happens, every single update needs to be incorporated. Because if we did that, then we would have concurrency issue to the exact problem that you mentioned. What happens if there are concurrent updates when I'm doing the merge? So again, so that's was the reason, is that I take a set of consecutively committed, they're done. I don't have to worry about it. And I don't care if there's other things that is happening right now. And I don't care if there's other things that I didn't consider. And that's fine too. Because I took these pages, and maybe the reason I didn't take this because there were some empty spots in this page, and I didn't want to dealing with an empty space of potentially even somebody inserting something into the page, even though I'm not looking at it. I didn't even want to do that. I don't even want to lock this page while I do my merge. So I only consider this set of pages, this set of records. And this doesn't necessarily have to contain every update. So that's for one thing. Now, second point. While I do this merge, I created my consolidated page. So what could happen is that this record, it's also starts getting updated. So it actually writes its third update. The merge didn't even consider the second update, let alone the third update. It's completely outside the scope of the merge. The merge has no effect on this because merge is done on the side on its own. And here, all we're doing is simply adding a new tail record, which is fine. There are two independent actions. They're nowhere on their paths they cross. There's no independent, they are completely independent of one another. And now, so what happens? So at the same time that this merge is happening, I continue update my records. I add the third version of the tail record. Now at the same time, what could happen is that what I did, I take that new record, I install it here, I make my page directory to point to it by installing it, meaning just making the page directory point to it. And then at the same time, that update transaction updated the indirection column let's say the transaction was committed, update its indirection column to point to the third tail record. So then what happened here is that, well, the update was happening completely independent. I didn't touch any of these pages. These pages were not included in merge. Merge didn't even touch those after the merge was done. The only thing that the merge did was to update the page directory. The only thing that the write transaction did was added the tail record and update the indirection column to point to this latest tail record. The path of the merge and the path of that write transaction are disjoint. They're not going to step on one another's toes. And that's why they can go ahead without any coordination. And it's also important that the merge process, we're only going to merge the base pages, the regular base pages that are read-only. The indirection column does not participate in merge. Indirection column has nothing to do with the merge. It never needs to be merged and has no effect on merge. So that's why, because the only place that there is a potential of concurrent access is the indirection column. It's because the only one is then an in-place update. The rest was always a stable data. It was always, this was read-only. This is also read-only at the time of the merge. So nobody's going to modify it. It's okay to read it, but nobody's going to modify it. And the reader are okay too, because the tail pages are kept around. And as far as we're concerned, the old base pages are kept around. So reader can always go ahead and read without any disruption. And so readers are not affected. And well, we're not writing to it, so there is no writer issue. The only thing that is actually write to it is that indirection entry. It's an in-place update, but it doesn't participate in the actual merge. It doesn't have any role in the merge. And of course, the new tail record that we added is not an in-place, but is an append only. But again, it didn't affect the merge because we had already settled what we're going to merge. And I could add as 1,000,000 records while I do the merge. They're simply ignored. And so then what becomes interesting is that the in-page lineage that we talked about. So when I come to this, when I look at this page and it has a lineage information, and the lineage information says, well, I only have consolidated the first 10 records. That means I don't know what this information is. So if you want to get the latest value, you have to look at what came after this merge was done. If you look at the in-page lineage of this is a 0. That means it doesn't see any of the records. So if you want to bring the value in here up to date, you have to look at every single tail record. So now, actually, let me make a pause here before I say the next step of this. Any question? Okay.
I have one question, I guess.
Sure.
During the squash process, where you're kind of going back over the lineage and constructing a new base page, like say you have 100,000 updates, is there any reason to go further back than after every single column has been updated once as you're traversing backwards?
So no, that's an excellent question, and that's an excellent optimization. So that's optimization. So now, when is it to stop? You may be unlucky that one record only was updated once, and that was the very first record. So you have to go back. But at least there is a termination criteria, is that if every record is regularly getting updated, then you may be able to skip many things. So there's a good pruning opportunity, as you see. So that's excellent observation. So now, so the other interesting thing is that, so now let's say all of this happened. Now I'm a query. I come from the page directory, and I get this this base page, and I see the base page has a lineage of 10. That means it's seen the first 10 updates. Okay. Now I want to read this record, and I look at the indirection of this record, and it points to the lid 15. So if I look at this lineage information, which is 10, and I look at the indirection table, the indirection value, which is 15, has this update been applied to this page or not? The indirection says I'm pointing to the 15 record. The in-page lineage tracking for this page says that I've seen the first 10 updates. Has this update applied to this yet or not? No. So that means if I come to across the situation that my in-page says my lineage is 10, my indirection is pointing to 15, that means since I did the merge or while I was doing the merge, the record got updated again. So to get the latest version of the record, I need to again follow the indirection and get that tail record. But if it was the case that my lineage information said I have it's 10, I look at the first 10 record and the read to the latest version says 5, then I know that already in this page, I have all the information. I no longer need to follow this pointer. So, and this becomes the importance of the merge. So if the merge can keep up, hopefully for most of the records, this consolidated pages has all the updates, so I no longer need to follow the indirection. And that will definitely save on, it will save us on query time, on reading. And the other interesting thing here is that if I'm reading from this page, the lineage information of this is 0, the indirection of it is still this, and the indirection says 15, well, I still have to go to this, and then I can go back and construct as needed. And by maintaining this lineage information within a page independently as the result of the merge, that means if here I could have one of my base page have a lineage information 10, seeing the first 10 updates. I have another base page that has a lineage 0. So that means it hasn't seen any updates. So to get the values in this page, I need to look up, but to get the latest value for this page, I don't need to look up, and that's fine. There is an inconsistency here, but the lineage information allows us to detect that inconsistency, and along with the indirection and the tail pages, I can bring all of these pages to a consistent view. They can all see the latest update. And that can be done by just going to the tail pages and bringing up the value up to date. So this allows us to even break the barrier or break the requirement when of doing a merge, do the merge of all the column of the base of the same page range at the same time. We don't even need to do that. All we need to do, each base page can actually be independently merged for every column. So again, so the idea is to eliminate any coordination, any linkage as much as possible. And that lineage information not only allows us to figure out the current state, it allows us to do this merge efficiently and completely asynchronously. And since this page maintains how many records it sees, it allows to relax the need of having every single update. It's okay. It just tells you already in it that it only seen the 10 updates. So it's okay if while the merge is happening, you go do another 5 updates. The page doesn't claim that it's seen it. And so that information is already incorporated in that, incorporated in its header. So again, that becomes crucial to have this contention-free design, which has been sort of the core motivating or inspiring for the work, for this entire work. Any question? So that's really completes the core of first milestone and the second milestone. Now, moving forward, we're going to look at concurrency, and the concurrency issues are mostly for some, there's limited concurrency issue because the merge we talked about, the merge can be really done asynchronously without any contention. I mean, the only contention is potentially in that page directory swapping that net pointer. It's possible that a reader comes to that page directory trying to read that element while we're swapping it. So there is one contention point in there, but overall there is not much of a concurrency happening in the merge. And contention, not I mean, things are happening concurrently, but there's no contention. And so that really captures the first two milestones. And then, well, the remainder or the next February, we're really going to really focus on concurrency and transaction, and that really all the materials needed to understand the core of the databases in terms of supporting concurrent user. But let's look at some evaluation. I mean, I know it's kind of, we're on top of the hour, but it's okay since it's recorded, you can view it. But I think this is important also. It's important that we learn how to do experimental evaluation and how to present our result. And that's something you can do also for your assignment. So if you really go out of sort of take that initiative and not only just show some preliminary results of your data, but also have graphs and show that you're doing analysis, figuring out what are the bottleneck of your system is, what is the strength of your system, and you can experimentally show that. That's a very valuable piece, and absolutely will be rewarded as part of that, getting up to 20% bonus for your assignment. So these experiments, a lot of them were done, I think, around 2018, 2017. And sort of the main hardware that was used, it was a single machine. It had 2 sockets. Each socket had 6 cores. And these are 2.2 gigahertz was the clock speed. And then 64 gigabyte was the size of main memory. And our L3 cache was 15 megabyte. And again, we have L3 cache, that's on top of the hierarchy. Well, we have L1 and L2, but L3, your main memory, your hard disk, your SSD, your main memory, your SSD, your hard disk, and potentially your tape. So that, again, that memory hierarchy. So that's important. When we do an experiment, we have to say what kind of machine it was used. What is how much memory we had. So again, those are important as part of to be able to replicate those experiments. And in terms of the workload, we used a workload that Microsoft Hackathon had kind of put together for their in-memory database, and we kind of extended it and add more sort of features and more variation to the workload. And what we also compared the approach with is that we did in-place update plus history. And so that's a kind of an approach that was inspired by how Oracle database was doing this consolidation. The other one is delta plus merge, but the merge is kind of blocking. That's a technique that SAP HANA, again, another major vendor, have been proposing and has been designing. So these are all kind of happened in mid-2010. So these different Oracle and SAP and other vendors. And so what we also studied, we looked at the effect of contention, we looked at varying the read-write ratio. So for example, a transaction may consist of 10 operations, and some of them are reads, some of them writes. Look at the variation. I mean, for our case right now, for first 2 milestones, there's no notion of like transaction, or we have a notion of transaction, but there are single statement and also a single user. So everything is kind of very simplified at this point. And then we look at the frequency of how not only that we're doing short update transaction, but also we do how frequently can do our merge, and also doing analytics in the background, like just scanning the data, scanning large amount of data. So long running queries versus short update transaction. And then we also looked at whether it's, because the outstore in its, if you just look at the lineage-based storage architecture, the idea of maintaining a lineage, I have a base page and I have a tail page. Base is the original, tail is the delta, and a lazy contention-free merge. That abstraction applies to row store, that abstraction applies to column store, that abstraction applies to document store, graph store. It's a very general abstraction. So it doesn't limit, it's not only for one particular type of data model. And then we also looked at comparison with key value stores, because key value store also have this very optimized way of handling writes. So lock structure file, so that's the basis of most key value store. Level DB is one example which is developed by Google. So these are kind of, this is our the experimental space. Again, for your assignment, of course, you're not expected to do such an extensive, but at least whatever you do is you exactly say what it is. What was it compared with? And it doesn't even have to be compared with anything. It could be just a self comparison. If you add your optimization or you don't, or you remove your optimization. So, for example, what is the base version of the throughput of your base method, and now the optimization was to add an index, what the effect on the throughput is, and the optimization is that you did something fancy with your merge. So now what is the result of the throughput? So that could be the kind of comparison that you can show, for example. So now the first experiment that I want to share is that, again, it's important to see what the graph means, again, for your result as well. So the y-axis, this shows throughput, how many transactions per second can be done. So up to 1 million transactions per second, or up to 2 million transactions per second. And the x-axis is the number of parallel update threads. So here up to, let's say, 25. So this machine, we can instantiate up to 12 threads. So if you remember, it was a 2 6-core machine. These are hyper-threaded, so that's 12 to 24. So it's about 24. So we have about 24 physical hardware thread, and that's why it's not even reaching 25. So we allocate one merge thread, so we really have 23 threads. So if you have up to 23 or 24 threads, so that means every one of those threads can take a transaction. So there are 24 transactions are being executed simultaneously. So as you increase the number of threads, naturally, you will have more contention, because there are 24 different transactions. And if those transactions and some of the data items are popular, if you have one transaction or you have 3 transactions, the likelihood that all 3 needs the same popular data item is less as if you have 24 transactions, and the likelihood that some of them will want that popular item becomes more. So that's why we see kind of a drop of a throughput as we increase the number of threads. This is a low contention graph. This is a medium. This is a high contention. So if the contention is not a whole lot, then, well, in fact, actually, so here we're not even seeing a decrease. We're actually seeing an increase. And the reason is that there's low contention, so adding more thread doesn't actually causes any race condition, or doesn't cause any locking issue. So having more threads, that means we are adding more hardware, we're adding more resources. So the more resources we add, the more hardware we add, the performance of all techniques improve. Not equally, but they all improve. But when we have a high contention, as we add more thread, the performance does drop, because now they have all these locking issues that is happening. And so contention increase, the performance drops, but the sort of the basic principle of design of LSTOR was to avoid those contentions. So that's why it's not affected by the contention that we're injecting into the workload. So we do see, I mean, up to 40 times performance benefit on this very highly contentious kind of network on workload. And the contention is not necessarily means that they are accessing the same record. That means they're accessing the same page, for example. And since we are dealing with compressed pages, and since we're dealing with column store, the number of records that can fit into a page is a lot more. So in your traditional row store, if I had a 4K page, then if each record was 100 bytes, then I could keep 40 records. So if I'm locking that page, I am locking out access to 40 other records. So 40 records are affected by that batch or by that lock. But if I'm talking about a column store that is only stores one value, one field, and it could be highly compressed, and in order to get even a better compression, I'm not going to just use a 4K page. I'm going to use a 64K page, because the bigger the page is, the better compression rate that I'm going to get. So in a 64K page it could be 8 times larger. The record could be 8 times smaller, and you could get some other X factor for compression. So a single page that I log, I'm going to affect now thousands and thousands of records. So there's a huge increase in the contention that I create if I were to log pages. And well, in the design of the LSTOR, we have eliminated all those because you have read-only pages or append-only pages. So all those locking contention has been eliminated, and that's what's kind of reflected here. So this is another important experiment, and this is kind of to bring that message, is that what if I kind of have a mixed OLTP and OLAP workload? The OLTP is my short update transaction, and the OLAP workloads are my sort of just scanning, just reading large amount of data. And what we are showing in this graph is the time to complete the scanning of the data, and it kind of ranges in seconds. And now, in terms of the setting, what we have 14 update threads. That means 14 threads are doing short update transaction concurrently. And then we have 4 OLTP. You can think of, we have 14 OLTP thread, and we have 4 OLAP threads. These 4 threads are doing scanning. So this is 14 update thread. This should say 4 scan threads. Actually, no, it is correct. So this is we're doing with 2 cases here. One case is that what is my scan performance when I only have 4 update threads? What is my scan performance when I have 14 update threads? So there's always just a single, we only have a single thread that does analysis, and we always have a single thread that does merges, and our page size is 32 kilobytes. So as we talked about, our standard page is 4 kilobytes, but in this environment, it makes sense to have much larger page sizes. So in this setting, we're using 32, and that's kind of also standard. 32, 64, it's kind of a sort of a standard page size when you're dealing with column store. So that's the reason, the choice of that. And we have a single merge thread, and that's important. So now let's look at the result, what the result means. And this is now what the axis is showing, is that every time I'm doing a merge, how many tail record do I take to do my merge? Do I take 4,000 record? Do I do 8,000? Do I do 32,000? Or I do 64,000? If I say I'm doing 4K, that means I'm doing a lot quicker batches of, I do a lot more merges more frequently, because every time I take a smaller amount. If I'm doing 64K, that means I'm going to try to wait enough tail pages gets accumulated, then I do my merge. And it's important is because every time I do a merge, I take a set of tail pages and I read all the base pages. So if I only take one tail record, that means for every one tail record, I'm going to try to merge it with every base page. So there's going to be a lot of overhead. But the more tail records that I have, it will amortize the cost of doing this this merge. So the more I batch, I get a better amortization cost. So that's why it makes sense to wait to get enough records. But if I wait too long, then it's going to deteriorate performance, because now the read code is going to really get slowed down, because there's so many tail records they need to examine when they do their scans. So there is a trade-off to make sure there's a good amortization of the cost of the merge per tail record, while without deteriorating the performance of the read because you had to wait too long for the merge to happen. So now, in this case, if I have lots of update happening, which is this the blue one, if I have lots of update happening, and the merge is only four records at a time, so many tail records are being created. I'm only doing 4K at a time, so it's not gonna scale. So my merge is my scan operation. Basically this says that the scan operations takes about 2.5 seconds, just because the merge, that single merge thread cannot keep up. There's just so many things to update. But as I increase the number of batches of tail record that I take before I do my update, I see this number increase. So the 32,000 seems to be the sweet spot. If I wait enough for 32,000, then I can substantially reduce the scan performance. That means the merge can now really nicely keep up without affecting the scan performance. So you get a nice amortization cost. For 64,000, I'm getting a nice amortization cost for my merge, but now the scan again going up because there's too many records. So that now there's all these records that are kind of outstanding. So this is if you have 14 update threads, this seems to be the sweet spot, a sweet spot between how much amortization I get without delaying the merge too long. And the green one, which only have 4 update threads, so there are not that many tail records that are being produced. So again, 4K seems to be, again, too high here, and the sweet spot here seems to be about 16K. So at 16K is probably the ideal situation. So if I'm in a workload that doesn't have too many updates, then I can do my merge more frequently. If I have the workload that's just generating a lot of updates, then I need to delay it a little bit more in order to allow my merge thread. So the merge thread can keep up at 16,000 at a time with this setting, but the merge thread really needs, here its best performance of it is at 32. Of course, you can always add a second or a third merge thread to help the process, but this is kind of showing the sort of the performance of the merge as well too. So kind of so many things happen here. The scan is happening, the merge is happening, and the update is happening. And this seems to be that kind of overall could be the sweet spot even for both workloads. And so this one is, this is another sort of, this is kind of the final graph that I want to share. Again, looking at, so the other one was a merge performance. This is the this is the performance, a more holistic performance of mixed workloads. So we have 17 thread and 1 merge thread. And so how we look at the distribution of these 17 threads is, so again, these are the different techniques, and these are the number of parallel update transactions. So if there is only 1 update transaction, that means I have 16, the total is always 17. So if I have 1 update transaction, that means I have 16 scan threads. If I have 12 update transaction, that means I only have 4 scan threads. If I have 16 update transaction, that means I only have a single scan thread. So this is a more OLTP workload. This is a more OLAP workload. And maybe here is somewhere kind of a mix OLTP OLAP. And so what this kind of shows is that the performance of updates as I increase the number of update transactions. Of course, if I have do more updates at the same time, my throughput goes higher. But of course, if I'm doing more updates, my contention increased. If my design cannot cope with contention, it will have a negative effect. And then finally, this is the exact same experiment, but it's just showing from the perspective of read-only transaction. So, and it's showing the read throughput as opposed to be the update throughput. So here, if I only have 1 read-only transaction, that means there are 16 update threads. Here, if I have 16 read-only transaction, that means 1 update thread. And again, the same thing is if I have more resources dedicated to scanning, well, I get a better performance. And otherwise, the performance will be lower. But in here, we see that when there is only one read-only transaction, the performance is really low. But one of the reasons for that is just because there is so much. So there's also a lot of contention that is happening. So that contention, not only there's not enough resources to do reads, but there's also a lot of contention that the system needs to handle. And so that's kind of partially explains that as well too. Okay, and so some of these are explained in more detail in the paper, and there's a bunch of other ones, and I think it's a good practice for you to start reading the papers now that you have seen the slides, you've seen the assignment, you've seen it in the discussion, we've spent good amounts of time on it. So now, if you haven't read the paper, go ahead and also read the paper. It's good, it's important that you create that self-independent mindset and ability that you can take any textbook or any research paper and you can distill it. And it's not going to be easy at first, and that's understandable. But after a while, reading enough papers, reading enough books, it becomes easier and easier over time. But it's an important skills to acquire, and I think now is the best time. And I think that's it. Any question? All right. So have a wonderful day, everybody. And I guess, well, we have an office hour, so I will switch to the other Zoom link for the office hours. So thank you, everyone. Have a great day.